Calculus, Chapter 2, Section 7, the slope of a tangent. I'm your host, Dr. D. Let's get started. Okay, had to get that last link in. The slope of the tangent. We started talking about this on the very first day of school. We've got a curve. And we've got a point on that curve, we'll call it point P. And the coordinates of point P are going to be a, f of a. So some x value, and you plug that x value into the function, so we have an x and a y value. Now, we realize that we need 2 points to get a slope. So what we do is we pick some other point on this same curve, and we call it Q, and that point is going to be some x value and some f of x value. So what's the slope of PQ? Well, that's change in y divided by change in x. So the change in y is f of x minus f of a. That's the distance we move up from P to Q. The change in x is going to be x minus a. So that's the amount we move over to get from P to Q. So we say the slope of PQ is f of x minus f of a over x minus a. Change in y divided by change in x. Okay, now the slope of the tangent at P. Remember the whole principle that we talked about. If we make this distance between P and Q smaller and smaller and smaller, so it's infinitesimally small, or as we make Q arbitrarily close to P, then the slope of PQ gets sufficiently close to the slope of the tangent at P. All right, so the slope of the tangent at P is going to be the limit as x approaches a. See, as x approaches a, that means we're moving Q closer to P. So the limit as x approaches a of f of x minus f of a over x minus a. That's it, piece of cake. Now that you guys are experts at evaluating limits, we're actually going to be able to find the slope of a tangent. We're actually going to be able to find the slope of a tangent. Okay, cruising onward. Now we have the exact same situation, only we're going to be using alternate notation. So once again, we have our curve, and we want the slope of the tangent at P, and point P is going to be a, f of a. Now, point Q is going to be a plus h, and f of a plus h. In other words, h is some x value that we're adding to get from P to Q. So that means the y value to get from P to Q is going to be from f of a to f of a plus h, where a plus h is my x value of Q. So my slope of PQ now is going to be the change in y, which is f of a plus h minus f of a, y minus y, over x minus x. Well, a plus h minus a is going to be just h. So, likewise, the slope of the tangent at P is going to be the limit as h approaches 0, the limit as Q gets closer and closer to P. So the limit as h approaches 0 of f of a plus h minus f of a over h. Now, we have both situations. We have lim is x approaches a of fx minus fa over x minus a. And we have the limit as h approaches 0 of fa plus h minus fa over h. Do you think it would be important for you to memorize both of these? Yes, I think it's important.
That's the smartest thing I've ever heard anyone say about anything.
Okay. So, it's time to get this concept locked in your brain and be able to use it. Okay, now let's do one more thing while we're talking about theory, and then we'll jump into some example problems. So, notice this is a general function that we're trying to find the slope of a tangent. Well, let's say this function was distance versus time. Okay, so we have time here, and we have distance here. Well, clearly, we can't have any negative time. We can't go back in time. Okay, so notice what's going on here. This is like a car that's starting off. Now, when you get in your car, you don't just immediately get up to 65 miles an hour. You get up to 65 miles an hour in a certain length of time. So notice what's going on with this blue curve. If this is distance and this is time, well, in the beginning, time is moving on, but I'm not getting very much distance. But as I move forward in time, my distance is going further and further, faster and faster. So what we see here is an increasing velocity. Well, what is velocity? It's distance divided by time. So velocity really is the slope of the tangent. Okay, so let's look at that. You've known from pre-algebra days that distance equals rate times time. So what we could do is we could say, okay, that means rate equals distance divided by time. Now rate, we know, is velocity. And we've been talking about average velocity. So, you know, with your Algebra 1 problems, the car traveled 60 miles in 2 hours. So what's its velocity? Well, we're talking average velocity there. So did the car go 30 miles an hour every single minute? No, it started out at 0 and it sped up, and then it slowed back down, sped up, slowed back down. So we have an average velocity, which is going to be the change in displacement, which means the total distance you've covered, divided by the change in time. So we could write that, well, first of all, S is what the variable for displacement. So S sub 2 minus S sub 1. So it's a particular displacement minus a displacement before it. So basically the change in displacement, this triangle is a Greek letter delta. It just basically means the change in displacement. How far have I gone? Divided by time 2 minus time 1, or a change in time. So change in displacement divided by change in time is going to give me the average velocity. Now, if I want to know the instantaneous velocity, so in other words, average velocity, I took a trip, I started at 2 o'clock and I finished my trip at 3 o'clock, and I could say I covered 60 miles in that hour. So my average velocity is going to be 60 miles divided by 1 hour, or 60 miles per hour. That's my average velocity. Well, what I want to know is, what's my instantaneous velocity, or what is my velocity at exactly 2:30? Not my average velocity over the whole hour, but how fast was I going at exactly 2:30? Well, if I want to know a specific time, then my change in time must approach 0, because I want one specific time. So my instantaneous velocity is the limit as delta t approaches 0 of delta s over delta t, which is going to be in miles per hour at a specific time. So notice average velocity is a velocity over a period of time, whereas instantaneous velocity is velocity at a particular instant in time. And remember, we need 2 points. So a particular instant, what we're doing is we're taking 2 points in time that are infinitesimally close to each other. So that basically is an instant in time. All right, so this is the whole concept of today's lesson, is that the slope of a tangent is going to be the limit as x approaches a of the slope of the secant, when the secant is x minus a apart from each other. Okay, so let's try some example problems. All right, take a look at example 1. Find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. Now, notice down here at figure 2, before we get started, if I look at a graph from 0 to 2, then I see the point 1, 1 is my curve. Now if I look at that same point and I zero in on it, I zoom in from 0.5 to 1.5, now notice my curve is starting to look a little flatter because I'm looking closer at it. Now if I look at it from 0.9 to 1.1, now it virtually looks like a straight line. Well, that's the principle of allowing a limit to approach 0. We're allowing our view of this curve to approach a very tiny space, and that's making the curve look like a straight line so we can get the slope of that straight line. Okay, let's look at our curve now. Okay, so here's our curve y equals x squared. And let's try something here. We want the slope of this curve right at 1, 1. So here's our point that we're looking for the slope of that curve. Now, we know that we're going to pick some other point on this curve that's going to be, well, here's 1, 1, let's do it in black. Okay, here's our 1, 1, and here's our x, f of x. Doesn't even matter what that point is. Now, the slope at this point is going to be the limit as x approaches 1 of the change in y, which is f of x minus 1 over x minus 1. Now, what's f of x? It's x squared. So let's plug that in. Okay, now you guys are experts at evaluating limits, so let's just crank this out. So let's plug in 1 for x and we get 1 minus 1 over 1 minus 1. Oh no! What do we do? This looks like something quite impossible. It's not really. All we do is factor this. So we have the limit as x approaches 1 of x plus 1 times x minus 1 over x minus 1. The x minus 1's cancel, and so we have the limit as x approaches 1 of just x plus 1. Now when you plug in a 1, you get 1 plus 1, which is 2, as they taught me back in first grade. Okay, so what we just found out is the slope of the tangent right here at that point, and we'll just stick with black. Nice. That slope is exactly 2. It's not approximately 2, it's exactly 2, because we took the limit as x approaches 1. So now, what we need is the equation of this tangent line. Okay, so that means we found a slope and we have a point. Well, let's plug it in point-slope form. So it's y minus the y value, which is 1, equals slope times x minus the x value. Just in case you guys forgot this, the point-slope form is y minus y sub 1 equals m times x minus x sub 1. Okay, so now all we do is distribute the 2. So y minus 1 equals 2x minus 2. Now we just add 1 to both sides. Y equals 2x minus 1. That's the equation of this tangent line, which, notice if I continue that down, it goes right through -1 perfectly. This is an amazing graph. And remember, if it looks at all crooked, it's merely the air density variations between you and the board. Okay. Okay, so that's it. That's how you get your slope, and that's how you get your equation of the tangent. Okay, cruising onward. Example 2. We've got y equals 3 over x, and we want the equation of the tangent line at the point 3, 1. So let's just do that. Okay, and we need to zoom out a little because we need the point 3,1. Okay, so what we're trying to do is find the equation of the tangent line. But you know what I'm going to do? I'm going to put the tangent line in here. This will be spectacular. Let's see. Y equals negative 1/3 x. Third x 2. Okay. Now that is spectacular. So we have the point 3,1, and we're trying to find, oops, craps. Cut, take 2. We'll edit that out. Okay, we have the point 3,1 right here. And that is a point on the curve y equals 3/x. And we want to find the equation of this tangent line, which is in fact perfectly drawn this time. And we don't even know how we got that. So we're gonna have to calculate that out. Okay, so this time we're gonna do it with the second form. So we've got the slope of the tangent is going to be the limit. Well, before we go there, let's just label our points. So we've got 3,1 right here, and we've got some other point. Let's just put the point up here. And this point is going to be 3 plus h. Oh, you know what? The fact we're going 3 plus h. Yeah, let's take 2. We're going to make, we could just say h was negative, but I'd rather not. I don't want to confuse you guys quite this early. So here's my h right there, or here's my other point right there. So what's that going to be? It's going to be some h value to the right. So it's going to be 3 plus h. And then it's f of 3 plus h. So what is f of 3 plus h? Well, yeah, let's just... Okay, the function is 3 over x. So, yeah, we'll just go f of 3 plus h for now. Okay, that's fine. So there's our point right here. It's some h value to the right, and then it's f of 3 plus h down. So, all right, back to the wrench now. So the slope at our 3,1 is going to equal the limit as h approaches 0 of f of 3 plus h minus the y value, which is 1, over 3 plus h minus 3, which is just h. All right, now, if f of x originally is 3 over x, then f of 3 plus h is going to equal 3 over 3 plus h. If you've got 3 over x as your function, I want to plug in 3 plus h. Now I have f of 3 plus h is 3 over 3 plus h. So that means my slope is going to equal the limit as h approaches 0 of 3 over 3 plus h minus 1 all divided by h. Okay, so let's allow h to approach 0 now. So let's just plug in 0 for h. Well, I have 3 over 3, which is 1, minus 1, which is 0, 0 over 0 again. So, once again, we have to do some work to get this where we can actually evaluate it. So, what I'm going to do is I'm going to get common denominators up on top. So, I have to make the common denominator 3 plus h. So, we've got the limit as h approaches 0 of 3 over 3 plus h minus 3 plus h over 3 plus h, all divided by h. Okay, now, let's fix the top. So that's going to be the limit as h approaches 0 of 3 minus 3, which is 0, now minus the h. So we have a negative h left up here over 3 plus h. Now, instead of dividing by h, let's just multiply by 1 over h. We're allowed to do that anytime we want. So, notice once again, the minus sign is subtracting the 3 and the h. So I'm left with 3 minus 3 minus h times, or then divided by 3 plus h, times my 1 over h here. All right, now you can see the h's cancel, and I'm left with the limit as h approaches 0 of negative 1 over 3 plus h. Now, you might be tempted to say, oh, let's not bother with this limit as h approaches 0 and just fix the fraction and then we'll figure out the limit. Do you think that would be a good idea? Do you think it would be a good idea? No, of course not. Yeah, we want to keep the limit all the way through here. Okay, now, let's evaluate this limit. As h approaches 0, this just approaches negative 1/3. So my slope equals negative 1/3. And that's the slope of this tangent line right here. Okay, now we didn't want just the slope, we wanted the equation of the tangent line. So that means we do the same thing we did before. Y minus y sub 1, which is 1, equals m times x minus x sub 1. Okay, now if I want to get that in slope-intercept form, all I do is distribute my negative 1/3, so I have y minus 1 equals negative 1/3 x plus 1. Now I add 1 to both sides, and I get y equals negative 1/3 x plus 2. Man, it's like I already knew that. How amazing is that? Okay, so this is your final answer. So, recapping the action. Well, rewind it and recap it for yourself. Okay. Now, let's get on to example 3. Find the slopes of the tangent lines to the graph of the function f of x equals square root of x at the points 1, 1, 4, 2, and 9, 3. Okay. That's kind of annoying. Cool.